All right, let's go ahead and get started. All right, so thanks for coming to this NPA late version today. Today we have Ryan Bouabid, and he's going to be talking to us about the Coherent collaboration. He's in his final year at the PhD at Duke and at my old lab. But Phil Barbeau, he's about to embark on a postdoc at Los Alamos, working on the Legend project. And he is also coming from the University of Chicago, and also did a postbac on Atlas, who's wide breadth of experiments. So take it away.
Yeah, thanks, Tyler. And yeah, thanks everyone for coming, and thank you so much for hosting me. It's been really cool seeing, all the kinds of incredible high impact university scale experiments that you guys are working on. This topic is going to be a slightly more low tech, but hopefully you'll find it interesting nonetheless. I'm going to start here with maybe a sort of canonical framing for what you want to do in a particle physics experiment, which is this sort of frustrating tension at the heart of the life of an experimentalist in this current day and age, which is that the standard model of particle physics is like this incredibly successful theory that describes all microscopic phenomena very well, that we're very happy with. But at the same time, we have this very strong body of evidence that we are convinced by that makes us feel like we need new physics. And the challenge, the central challenge of this moment is that the new physics that we're sure must exist has the characteristic that it has really manifest indirect properties. So we have all these indirect arguments that make us think that this new physics must exist, but it has really subtle direct properties. And so that means that when you go to look for it, you don't find it in the lab. And so that's sort of the framing that motivates the type of question that I'm going to talk about today, which is, can you use neutrino scattering experiments to lead us to new physics? And the way that you might get there is that neutrinos have like a long history in modern particle physics for revealing new and interesting phenomena. And so the idea is, if you do a really good job of looking at how neutrinos interact with matter, can you stumble on something exciting? So to get there, I'm going to first orient you to the wide world of sources of neutrinos, both natural and artificial, made here on Earth. And kind of remarkably, neutrinos span this absurd range of energies that you could find here on Earth, down from the impossibly small to observe all the way to the possibly large to even conceive of. And of course, with every one of those neutrinos, you also need to think about how likely they are to interact with matter. So where the red here represented the flux of those neutrinos, their abundance that you might encounter in an experiment here on Earth, the blue is a really rough cartoon of its likelihood to interact with matter if you were to set up an experiment. And as a general rule of thumb, I mean, as you get more energetic, the neutrinos are more likely to interact with matter. And so you can look at this this wide tapestry and think, what's the best sort of range to zoom in on if you want to use neutrino scattering itself as the probe for new physics? So I've smeared out most of the really low energy and extremely high energy stuff, because what's left in the white here represent the rough fuzzy bounds of the lowest energy neutrinos ever detected and the highest energy neutrino ever detected. Both bounds are fuzzy, funnily enough, because we don't know exactly what the lowest one is or the highest one is, but we can infer guesses based off the technological constraints of both experiments. So the lowest ones come from radiochemistry, and the highest ones come from these neutrino telescopes. But so that leaves us a pretty wide range to think about of, still here, all these different kinds of neutrinos that you could go after to build an ideal precision experiment to look for new physics or deviations from the standard model in general. But I'm going to break it down with a heuristic here that might be useful to think about, broadly speaking, into three categories. So at the very highest energies, you have these somewhat clean predictions, though maybe not ideally clean. But the problem is that the neutrinos at those energies are quite rare. And so you might wait a while waiting for those neutrinos to interact in your experiment and to characterize the properties of those interactions. At the middle range of energies, terrestrially, we have amazing accelerator sources. So these are your booster neutrino beams that can give you millions and millions of counts over the course of the lifetime of an experiment and great statistics. But the problem is that the predictions themselves of those neutrino interactions with matter at those ranges of energies are very messy. And that's because you're squarely in the regime of non-perturbative QCD, and it's like very hard to model exactly what's happening when you blow up the nucleus at those energies. And so it's great for a lot of things. So those sources are great for a lot of things, but to study the neutrino scattering itself, those are not the optimal range of energies. And then all the way down at the lowest of energies, you once again recover these really clean predictions because you actually don't resolve the inner bits of the nucleus. You treat the nucleus as a fundamental particle, and you get these really great predictions in the standard model. The flip side of that coin, though, is that these events are technologically challenging to observe because at these low energies, the observables are tricky. So I'm going to focus on these low energy neutrinos. That's like the framing for what's to come. And at these really low energies, we can like pretend like we're Enrico Fermi, and we can just draw these like simple interactions, ignoring all of the inner physics of what's going on in that contact. And we're just going to imagine like we have some neutrino coming in, it bounces off some particle, in this case a nucleus, and some neutrino comes out. And what we look for is whatever observable is relevant in that case, oftentimes for us, just some sort of recoil. Now, the game that we want to play here is we want to have really clean predictions to make these like precise measurements. These really clean predictions, and we want to have also these really clean measurements. And we really want to stay away from anything nuclear physics, because whenever you have nuclear physics coming into your measurement, then you're going to throw out your ability to make a clean prediction. And the goal here is to look for any daylight, to look for some deviation from the prediction if you can make this kind of measurement. And that's where new physics might show up in the neutrino sector. So this is like one strategy that the community can take to find something maybe a bit inspiring and beyond the standard model. So the process I'm going to talk to you about is this ubiquitous natural probe at the scale of terrestrial neutrinos called Coherent Elastic Neutrino-Nucleus Scattering, or the acronym in the field is CEvNS, that has a lot of connections to all sorts of different applications in the field of low energy particle physics. When I say it's like this natural probe at the terrestrial scale, what I mean is that it has the largest cross-section of any of these low energy neutrino-nuclear interactions. And so that means that if you can get a detector sensitive enough to see these really small signals, then you can get these like large event rates with relatively small detectors. And so in this plot here, just versus neutrino energy on the scales that might be relevant to us as like these like low energy neutrino physicists in the single to tens of mega electron volts is the cross section of a handful of interactions. Maybe like the canonical interaction that led to the discovery of the neutrino is this dark red line here, inverse beta decay, and several orders of magnitude above that is the coherent elastic neutrino-nucleus scattering process on some heavy isotope like cesium iodide. The flip side of that really high rate is that the signals themselves are quite small. So what we're looking for is a neutrino bumping into a nucleus, the nucleus recoiling in phase, and the very small recoil energies that are deposited into whatever target you're looking for on the scale of single to tens of kilo electron volts. So on this plot here, I'm showing you the recoil spectra, which you can think of as if you had a smattering of these events happening in your detector for a monoenergetic 30 MeV neutrino source, how those recoil events would be distributed. And as you can tell, the vast majority of them are quite low energy in what was previously a pretty hard to detect regime of energy. A few more things about the CEvNS process in general. For one, like I mentioned before, it's very cleanly predicted in the standard model, controlled at the percent level or better, depending on the recoil energy. And it gets this really large enhancement in rate that we talked about before from the weak charge, which will scale like in this particular case, the number of neutrons squared. So the more neutrons you pile into your target, the larger the enhancement of this process is, and the more abundant that event is in your detector. Okay, so let's say you wanted to go ahead and build a CEvNS experiment and look for conducting some sort of precision CEvNS test. Like you want to get as good a measurement of CEvNS as possible. You could go to a bunch of different places. You could also just wait around for something interesting to happen, like a supernova. But the source that I'm going to talk to you about in particular is these pion decay sources, of which there are a handful in the world. But in particular, there's one pion decay source that is uniquely good. And that's the one that where we conduct these experiments. So the Spallation Neutron Source at Oak Ridge National Lab is a Department of Energy basic energy science user facility. That is a great place to do neutron science. People go there to do things like neutron imaging of materials, all sorts of interesting applied material science, energy science, medical work. But I'll just tell you a little bit about how the place works in general, then why it's relevant to us. So the heart of the SNS is a proton accelerator facility that accelerates protons to about 1 GeV. Those protons are bunched and accumulated in a ring and then delivered to a mercury target at 60 times a second with a really tight, narrow window. And there are some things about this source that I'll point out as we go that make it pretty good even compared to other spallation neutron sources in the world. But so this schematic just roughly illustrates how the facility works. What's particularly nice about the spallation neutron source is the sort of unintended byproduct of the production of neutrinos within the source itself. So the source is like this big liquid mercury target. And when those protons smash into it, they spallate these mercury atoms and make a bunch of neutrons. But what they also do is create a bunch of pions that at these energies all come to a rest, come to a stop in the mercury. And when those pions decay, they fall, specifically when they decay at rest, they have a very clean, predictable 2- and 3-body kinematic decay chains that give us these really nice, well-understood energies of neutrinos. And in particular, there's this flavor breakdown of these like prompt muon neutrinos and then these delayed electron and anti-muon neutrinos. So these are their spectra and energy. This is the timing structure of the production of those neutrinos. So when the protons hit the mercury at 60 hertz, what you get is these prompt muon neutrinos in time with the proton beam. And then following the characteristic half-life of the muon decay, you get these delayed neutrinos as well. But what's remarkable is that compared to other spallation neutron sources, because the proton beam at the SNS is so tight, with like a resolution on the scale of like maybe like half a microsecond, then you get this incredible background rejection factor if you only look in time with the beam for your neutrinos on the scale of a few times 10 to the -4. And so it turns this neutrino source that has a sort of modest flux of neutrinos into this really amazing place to reject backgrounds. That being said, ignoring the types of steady state backgrounds, the last thing that you'd want to think about is whatever can come along with a beam. Like that story that I just told you is all well and good, but if you are just swamped with stuff coming off the beam, then you wouldn't get any of that advantage of that background rejection from the timing. And so the last piece of the puzzle that like is the key to even using this facility to do neutrino science is having enough stuff in between you and the target that can tamp down anything related to the beam that isn't neutrinos. And so in particular, the background that you might care about are neutrons that could also recoil in your detector weakly and mimic a signal that looks like a neutrino. And it turns out within the Spallation Neutron Source building, there is in a sub-basement an area that has extremely neutron quiet backgrounds that have been very well measured and characterized by folks at the SNS. That area has been lovingly dubbed Neutrino Alley, and it is a very small sub-basement like service corridor that has been repurposed as a makeshift neutrino facility under the strict condition that experiments, not pass a 3-foot egress off the wall. So besides that one technical challenge, it's like an ideal place to deploy neutrino experiments for this kind of thing. And so the The neutron fluxes down here, like I said, are extremely quiet, and that's just, I guess, by coincidence of the way this building was built. There is something like, I think 40 interactions lengths of concrete and gravel backfill between this hallway and where the target is, on line of sight, that damps down all those neutron backgrounds by orders and orders of magnitude compared to the top floor of the building. So this is a good place to do these kinds of experiments. These are the folks that conduct those experiments in large part. One of them sitting in the room right now. So the Coherent collaboration is an international collaboration of a couple dozen institutions and a bunch of little modular subdetector systems that work on their favorite pet project. The collaboration has had a string of hits, starting with the first observation ever of coherent elastic neutrino-nucleus scattering on cesium iodide in 2017, with a follow-up measurement, which was the second ever measurement of CEvNS on argon. And finally, our third observation of CEvNS on a germanium target, which is what I'll be focusing on here for the next middle chunk, telling you all about my work on the germanium system. So the story of looking for nuclear recoils in high purity germanium detectors is, I guess, quite a bit older than I had realized. The story starts with dark matter searches in the 80s and 90s, where folks developed low noise germanium detectors at Lawrence Berkeley to look for dark matter scatters in particular. But the idea is the exact same, because this sort of like WIMP dark matter scattering is like these low energy nuclear recoils. And this is the exact same type of technology that we've used to our advantage, like a couple decades later, to look for neutrino recoils instead of dark matter recoils. So this is what the germanium detector system that Coherent deployed looks like in a handful of different views. As a cartoon on the right here, you can see that it's an array of high purity germanium detectors that are surrounded by a pretty compact multi-layer shielding package full of like high Z and low Z material to knock down backgrounds, as well as an active muon veto panel surrounding the whole thing. On the top left here, you can see it like fully closed up, sitting no more than 3 feet off that wall. And in the bottom left here is what it looks like in an intermediate stage of assembly. Those copper cryostats are what hold our 2 kilogram crystals that we use to look for these nuclear recoils. So just a little bit more about those crystals. The germanium detectors that we use are inverse coax point contact detectors. They are germanium detectors that are cryogenically cooled down to liquid nitrogen temperatures, where they are semiconducting. And the specific nature of the I, C, P, and C just refer to the shape that the crystals pulled in, so that we can make them that big. Like 2 kilograms is quite big for these kinds of detectors. And the PC part, the point contact, is that low noise part that lets us get after these really low recoils, low energy recoils. So on that front, the table here just tells you how big these are. They're all pretty big. But in particular, the pulsar full of half max here is like a measurement of the electronic noise in these detectors. And all the detectors here have, somewhat close to state-of-the-art noise characteristics for these high purity germanium detectors on the scale of 150 electron volts or better. Right, so this is just a flavor of what the data collection at the Spallation Neutron Source looks like. Once you've got these detectors, you've packaged them in the shielding, you turn it on. What are you trying to do? So what's important is you want to look for neutrinos in time with the beam. So the data acquisition system relies on timing signals from the SNS to only trigger when we expect neutrinos to come in. So this is like in red here is like the signal window at 60 hertz. And on a trace, like, the output of a preamp on board these detectors, this corresponds to like this region in time of our waveforms where we're expecting neutrinos to come in. Very rarely, but that's where they can come in. And then at the same time, we'll trigger 60 more hertz for a total of 120 in these off-beam periods where we can collect a measurement of the steady state background. So that's a really, really big pulse. That's not what neutrinos are going to look like in our detector. This is a lot more of what the events are going to look like, much closer to the noise threshold. So this is an example of a 1.5 keV electron equivalent recoil in one of our germanium detectors. And this is just giving you a flavor of the types of features that we want to extract out of these types of events. So in particular, we want to know what the energy was with pretty high fidelity. Because we're doing this experiment in time with the beam, we also want to know when that event happened. So this is also a challenge when you start getting closer and closer to the noise. In particular, for this analysis that I'm going to tell you about, we limited ourselves to events no smaller than this. So 1.5 keV and above. And for that first pass, we found that the limitation was just how accurately we could reconstruct the onset of the pulse, more so than the amplitude of the pulse, for what that's worth. So this is a view of our backgrounds for the analysis I'm going to show you between the regions of interest of 1.5 keV and 20 keV, where we're expecting to see some sevens counts. In particular, I just want to emphasize that at this particular location where this detector was deployed, and for this amount of exposure, we expected negligible beam-related backgrounds. And we can say that somewhat confidently because this is the exact location that the cesium iodide detector was deployed for the first measurement, where the neutron-related backgrounds were quite extensively measured. And so we were pretty confident that the only thing that we were fighting here were the steady-state backgrounds that are, of course, measured out of phase with the beam. The last two things that I want to tell you before I show you what we found was how we come up with a signal prediction as well. So we talked about the backgrounds, like what are the signals like? So when a neutrino scatters in your detector, what's of course happening is that you get some amount of recoil energy, but not all of that recoil energy is observable. And we rely on dedicated detector response measurements to go from whatever the true recoil energy is to the observable recoil energy, what people in the sevens world or in the dark matter community call electron equivalent, as opposed to nuclear recoil scale. And so this is extensively measured in germanium detectors in particular, and we have a very good model with negligible systematic uncertainties on how to convert from one to the other in germanium. And this plot on the left here shows for the flux at the SNS, what kind of electron equivalent recoils we were expecting to see in our detector, with a reminder that our threshold was somewhere around here at like 1.5 keV. So like from here on is what we could expect to see in our detectors. The other piece of that pie, like I mentioned, was the timing reconstruction of those events. So germanium detectors, especially these larger 2 kilogram germanium detectors, have these like pretty slow drift times. And so on the upper right here are measured drift times for the detectors that we used in this analysis. That just mean like when the actual event happened, how long did it take to arrive at the signal readout? If that can happen on the time scale of several microseconds in germanium, especially with crystals this size. And so that convolved with the timing spectrum of the SNS neutrinos gives you an expectation of when to expect that arrival of these events. And so putting all of those together, man, it's not as bright as I thought it would be. Putting all those together, this is straight up our data. So this is on the left, a 2D histogram of energy and time of the events that came in time with the beam, and then one-to-one comparison of what came out of time with the beam. And in particular, the most sensitivity that you get out of this whole square is just right here, like early-ish in the arrival time and low-ish energy, because all of those recoil spectra die off pretty quickly. And if you just take this little box and that little box, you do a counting experiment, you'll find 21 counts extra, like a naive counting experiment, which is off to a good start. If you do something more robust and you do some sort of sophisticated 2-dimensional unbid maximum likelihood estimate, and you subtract off whatever you fit as the steady state background, you get something like this. So this is, believe it or not, what discovery looks like for us. This is, it turns out, a 3.9 sigma rejection of the null hypothesis of no sevens with a best fit of 20 counts, plus or minus a chunk, which lined up pretty well with our just the naive counting experiment. Yeah, please.
How do you separate out in the previous slide and the two where you have like the two flavors of neutrinos that you're checking?
Yeah.
How do you separate out these two, the blue and red histograms? Since
Yeah, we didn't fit the amplitude separately, but this is just breaking down for the total rate what the relative contribution is expected to be.
okay, but in the previous plot where you had the time distribution, yeah, you have like this overall histogram of the arrival times, and then you like divide it into these two histograms. How do you do that?
Yeah, so from the beam itself, we know that the prompt neutrinos are primarily muon neutrinos, and the delayed neutrinos are a combination of anti-muon and electron neutrinos. A detector that's got really great timing reconstruction, like a scintillator, with a pretty good estimate of when the events happen, can fit out with enough statistics the different contributions of the different components.
I guess I'm like, the part that I'm confused is that you're saying that you're separating them by the time, but these are like completely overlapping in time.
Oh yeah, absolutely. In the germanium detector, we just fit the total neutrino expectation. I mean, like what our black here is like the expectation of how many events we should get and when they should come in time.
Oh, this is just like an expectation.
Yeah, this is the signal prediction. This is
And the same thing in the data, you overplotted what given the number of detections.
Exactly.
Okay.
Exactly.
All right.
That's exactly right. Yeah. No, thanks for that. Right. So this is a pretty good start. This is 20 counts. We're obviously not stopping here, but this was, I mean, kind of remarkably, with just something like 8 weeks of beam time, the backgrounds of the experiment were low enough that we could get a pretty happy result of seeing the first instances of sevens on germanium. Funnily enough, we were just a little bit shy of the standard model, maybe like a 1 in 20 fluke, something like that. But we're collecting a lot more data right now, and with the hopes of coming up with a follow-on really shortly, which I have every expectation will line up a lot better with the standard model, but boy, wouldn't it be fun if it didn't. So that's what's going on in the world of germanium for the Coherent collaboration. Yeah, of course, this is just the error budget for that particular measurement that that we made. We're ridiculously shy on statistics, and that's the first thing that we're doing. We're actively collecting data right now with the expectation of maybe more than doubling or tripling this data set in the coming year. The thing that you might like fantasize about with this particular technology is like, well, how could you scale it up at the SNS? So in particular, I mean, this is what our detectors look like when they're outside of their shielding package. If you really want to go crazy with getting a lot of stats of these kinds of events, you'd want to maybe like compactly assemble them in some sort of array. This is a picture of the Legend 200 experiment that's currently running in Ground Sasso to look for neutrino cell beta decay. And so the only point here I wanted to make is that like the technology to scale up these germanium detectors is possible. We obviously don't have the same types of radio purity constraints that one would have in a double beta decay experiment. But thinking about how to like adapt this for the SNS is like sort of a direction that you could go in if you wanted to really make a precise measurement. If you like let yourself fantasize about what that could look like at the Spallation Neutron Source, you can do all sorts of really cool physics. I picked one example here that might be familiar to some of the people working on Atlas in particular. But if you if you cook up some crazy ideas about what sort of extensions to the standard model you can let yourself think about, then there are these right-handed, maybe light Z prime mediators that some pheno folks like to think about in particular when they're looking for explanations for the G-2 anomaly. And it turns out that with coherent elastic neutrino-nucleus scattering, you're extremely sensitive to the lightest ends in a very complementary way to the LHC, the lightest ends of these boson masses. And this is just some exclusion plots for like future sensitivities for this particular detector at various stages of its ability to upgrade that I could maybe talk about in the next couple slides. But there's a lot of interesting physics that you can do with this particular data set, these germanium detectors let you go at these really low energy recoils where you're sensitive to some sort of new exotic physics. So the last thing I'll say here on germanium is that the data releases in general for Coherent have been like a field day for phenomenologists. So like one thing that the collaboration has done a really great job of is putting out all of our data as soon as we can. And this is just a little histogram here of what folks in the pheno community like writing papers about that I put together using the CEvNS data set. And in particular, it seems like the strong winners are, at least right now, what seems to be trendy is electromagnetic properties of the neutrino. So like corrections to the CEvNS recoil spectrum, if you like let it have an enhanced magnetic moment, or if you let it have some non-zero charge. And also exotic modifications of the weak interaction. So like that Z prime example that I gave you, or non-standard interactions are like things that pheno people really like to think about. So there's a wide range of applications for this data, and we're not collecting it fast enough, but we're trying. The next part that I want to tell you about here is our ultimate limit at the current moment of precision is dominated once again by nuclear physics or strong physics, more generally speaking. So our understanding of the neutrino flux at the SNS is limited by our ability to model the pion production when the protons smash into the mercury. And that's like a common problem across lots of neutrino flux predictions, is that the nuclear physics ends up getting pretty tricky. But rather than try to model it better or get at those specific production mechanisms in a more precise way, the strategy the collaboration is taking is to normalize the flux with a different type of neutrino-nucleus interaction. So there is a specific type of interaction where a neutrino inelastically scatters on a deuterium nucleus, and all of our colleagues in the theory community tell us that they can make that calculation as precise as we want it, but right now it stands at the couple percent level. And so the idea is, if you have a really high stats measurement of this ancillary process that we're not using to probe for new physics, if you can measure that really precisely, then you can get the flux uncertainty down to whatever precision you have on your measurement of that cross-section. And so in our case, the goal is to get it down to the couple of percent level from where it stands currently at the 10% level. The collaboration has put together a big D2O acrylic vessel that that's currently taking data, and the plan is to use like an identical vessel but fill it with H2O just to cancel out some of the nasty systematics related to oxygen and whatever else might come along with the detector. And so that's currently ongoing, and that's the strategy to get those systematics down as low as possible for all the CEvNS measurements that are ongoing. The really exciting upcoming measurement that the collaboration is currently working on is the nearly ton scale liquid argon single phase calorimeter that is just now at Oak Ridge being commissioned. And what's kind of mind blowing to think about with this particular detector is that it's going to be seeing several thousands of CEvNS counts per year. So coming from a world of getting really excited about seeing 20 counts, it's hard to imagine what a flow with like 5,000 counts in your analysis looks like, but this lets you get an unprecedented precision, statistical precision on the CEvNS cross-section, which lets you do all sorts of really exciting physics as well. Beyond that, the collaboration is deploying a several ton scale sodium iodide array that commissioning is also ongoing. What's pretty exciting about this kind of measurement, if you can measure CEvNS on sodium, the rate is much lower, which is like highlighted here in this plot on the bottom left that scales the cross-section by neutron number. But if you can get at it, you can probe completely unique physics to the heavier isotopes. And in particular, you can get at some of the axial vector couplings that are really interesting and haven't been really touched yet by the existing CEvNS experiments. Beyond the CEvNS measurements the collaboration is working on, there is an ongoing inelastic program at the SNS, which at first glance appears to not quite be in line with this idea of doing this precise science with these really clean cross-sections. It goes against everything I said in the intro here about staying away from the nuclear physics, but there's actually a really compelling story here as well. This effort grew out of a lot of ancillary side projects to get after specific hypotheses about backgrounds at the SNS. But it's turned into like a really rich and interesting physics program in and of its own right. So this is the first inclusive cross-section of inelastic scattering on iodine 127 was produced by the collaboration. The time scale experiment that's following up is also going to make a pretty precise measurement of this reaction. There is like a fully dedicated inelastic program now with several ton scale inelastic detectors being deployed. But what's interesting in particular, I'll just give you like 2 details quickly about this, and then I'll wrap up because I think I'm getting pretty close on time here. But yeah, if you add these measurements in combination with the CEvNS measurements, it adds like this incredible richness to the science program in ways that are maybe not immediately obvious, but I'll give you 2 examples here. So the first one is thinking about supernova neutrinos. So if we're lucky enough, I guess you guys must have also gotten those like Slack gossip about that false alarm supernova a couple of weeks ago. But if we're lucky enough to see the next supernova when all of our big kiloton detectors are online, then thinking about what the neutrinos that we measure from those events mean for the actual supernova processes themselves requires having a pretty precise understanding of the cross sections at these energies. And what's pretty exciting is that the SNS is a pretty good place, about as good as it can get to measure those inelastic cross sections on Earth, so that when a supernova does happen, you can say something about the flux of the neutrinos that came off of it. So in particular, what you'd really want to do in line with the planned large-scale argon and water-based detectors that have the best chance of making precise supernova measurements is you want to build dedicated liquid argon inelastic detectors and water-based inelastic detectors where you can measure those cross-sections here on Earth and then have a great calibration for Dune and Hyper-K when that supernova goes off. The last bit that I'll leave you with in terms of like the exciting physics reach is that when you start having both these neutral current channels of interaction like CEvNS and charge current channels of interactions like these inelastic scattering processes, you can do all sorts of like cool flavor oscillation physics. And so, I mean, it's no surprise in general that spallation neutron sources should be a good place to do tests of sterile neutrinos because spallation neutron sources play a large role in the creation of the study of sterile neutrinos in general with the LSMD anomaly. But it turns out that the SNS is a great place to do this. If in particular, you can deploy both CEvNS experiments and large charge current experiments. The future of the SNS is literally getting brighter. The beam is on a steady path of upgrading. We're like somewhere right here in the middle with almost double what the power production was when the facility turned on. And more power for us means more neutrinos. So things are ramping up with an ultimate goal of getting to 2 megawatts where we're currently at 1.8. And maybe in the far future, the ultimate plan is to have 2 target stations at the SNS, which in our case would create this sort of ideal test bed for doing oscillation phenomenon studies, because you'll have these like very controlled multiple baseline sources of neutrinos coming in at different times. And so thinking far enough into the future, you can imagine deploying these like large scale multi-ton water or liquid argon detectors that can not only do interesting supernova calibrations, but also some exciting oscillation phenomena studies. Yeah, so that's all I'll leave you on. There's a lot of cool things that you can do at the SNS. We're just getting started. There's a really broad impact of a pion decay at rest program that touches on nuclear physics, high energy physics, astrophysics, and as long as we can make these quality measurements at this place, then there's lots more to do and lots more to say about the underlying physics. So thanks a lot.
All right, thank you for the wonderful talk. We have time for some questions.
Yeah, so I might have missed this, but are there any analysis like procedure that you do for background rejection, or is it just that you're subtracting the offline from online?
Yeah. So for the germanium results for this first analysis, all we did was subtract the off beam from the on beam. We applied no PSD. It's just purely from timing. for the upcoming analysis that we're currently working on, we're hoping to apply some PSD to enhance our background rejection, because there are clear sources of background that we know are present in our data. But for the first analysis, we thought it was sufficient to just put out that result as it was, just do the easiest thing.
I see it. So when you do your statistical analysis, how many background events does it get, like the best fit?
It's about 1-to-1.
Okay.
And you have a plot of your background at one point, and there was like a big peak at like 10.
Yeah.
You know what that's from?
Totally, yeah. So this is a cosmogenically activated isotope of germanium. So when you keep these detectors on the surface, you can get some activation. And those have like a characteristic half-life. But we also just have no sensitivity in this region as a result of those dominant peaks.
Okay,
So we just excluded it from the analysis.
I see, so that's just like a natural radioactive decay.
Yeah, yeah. Yeah, inside the detector itself. And then there's a peak right next to it of like some zinc near the cryostat that's also getting activated just constantly.
I think you did touch on it, but I might have not caught it. The D2O stuff
Mhm.
that's not gonna tell us anything about sevens. It's going to try to probe like the flux uncertainties from the beam.
Yeah, exactly.
right?
Yeah, yeah. So I mean, it can also do interesting physics in its own right, but the main application that we're looking for is getting a better handle on like normalizing the flux.
I have a question on this,
Mhm.
sorry.
Nope.
So what kind of mass of DO and HDO do you have?
Yeah, so I think it's something like 700 kilograms of very high purity D2O and about the same amount of water in the same type of vessel.
Are you getting it from like Canada, like same sources?
I actually don't know
Okay.
where it's being sourced from. I think I have a feeling that it's actually DOE D2O that's been aggregated and was sitting around Oak Ridge and then used for this in particular. So I think it's ours. I mean, ours, America's.
Nuclear something.
Yeah.
Cool, so what kind of precision and math do you need to get to the to do this measurement to 3%?
Yeah, I think that the expectation is something like a couple years of exposure is enough stats to get to that type of precision with that amount of D2O, and then provided there's no unforeseen horrible systematics in the analysis that related to the light collection or things like that.
Some precision of the D2O.
Yeah.
So, yeah, if they need it, so, Diet Bay, as a person developed this like super 1% level, scale to measure the liquid scintillator, that they had, you know, but I think this is a much smaller, so it's gonna be easier.
Right.
to tell.
Yeah. At least for this benchmark goal of 3, if there's a desire to go further, I mean, the theorists say they can do better than 3. Like in terms of, the 3 number comes from what is currently in the literature of how well the theorists predicted. But it seems like from conversations, people think they could do even better. But then it's like our job to catch up to that as the experimentalists.
So to also follow up, is the reason like doing this on water and heavy water is better than germanium is just because the nuclear physics is better understood for those
Yeah.
things? Okay.
Totally. So like if you had the same amount of germanium, you'd get way more inelastic scatters on the germanium than you do on the deuterium, just because the nucleus is a bigger target. But modeling the germanium inelastics is nasty.
Yeah.
Why is the SNS pulse at 60 hertz? Seems odd.
Yeah,
Is it locked to the power line or is it?
I don't think so.
Yeah,
Plug
okay,
into the wall.
yeah, that's just struck me as odd.
Yeah, you're not the first person to make that comment, but I don't know. I
Okay.
wish I had an answer. I should actually.
Yeah, it's like I would pick any other frequency,
Well,
but maybe it's.
Technically, it's like 59.9 something. I don't know. They drop a pulse every 10 or something like that.
Yeah, interesting.
Sort of coming from the precision measurement.
I know, I'm thinking maybe everyone who uses particle accelerators just knows this and I'm just in the dark here. but-
There wouldn't be discoveries.
You can't do any like, you can't do any Fourier, you know, FFT.
Yeah, exactly.
Yeah, so relates this, so if you got to the like 3,000 or 5,000 counts in liquid argon, would you then be limited by this 3%? And the rest of your systematics, like at what statistical uncertainty do you become? You need to push further from there.
Yeah, so in both let me see if I can go to the slide. Just to have them up here. Right, so in each of these different sevens measurements had their own error budgets. For the cesium iodide measurement, for example, one of the dominant systematics was how well they modeled the nuclear recoil quenching factor, like the detector response characterization. And so there were like dedicated, ancillary measurements to knock down that systematic uncertainty. In Argon, there were some systematics related to the pulse shape discrimination and the analysis itself. All of these, like together, all the different analysis systematics always end up being between like 1 and 10-ish%. The flux was the dominant systematic, but we don't have, I don't think we don't have an experiment right now that has everything below 3 in terms of the other systematics. So
But they're all dominated by the uncertainty and the flux.
at the moment, yeah. I mean, the germanium result is dominated by the uncertainty of the stats, but when it won't be, it'll also be dominated by the uncertainty in the flux. So for the coming, 5 or so years, the flux uncertainty will dominate for all of the experiments.
Oh, no.
So do you have any comment on the quantum flux figures?
Yeah, absolutely. So the CONUS plus results, and I guess also maybe the xenon results, but I'll just talk about CONUS since you mentioned it. The postdoc in our group was a member of the CONUS collaboration, and so we're all really happy that they made that landmark achievement of a really great measurement of sevens at a nuclear reactor, which has been like something that's eluded the sevens community for a long time. They use the same type of technology as we do. What let them make that reactor measurement, which is way harder than this SNS measurement, is that their germanium detectors are even lower noise than ours. They really push the thresholds down. Their analysis thresholds in electron equivalent units were down to like 200 electron volts, where we were living up there at 1.5 keV. And to do that kind of thing, you really need to work really hard. I mean, you need to really understand your noise as it evolves throughout the lifetime of your experiment. And to do that at a reactor is even harder. So yeah, I mean, it's a really great result and great for the community in general.
All right, well, if we any more questions we can take offline. Can we thank the speaker one more time?